Welcome to the AI Research Roundup. I'm Alex, and today we're looking at this paper from the Hugging Face trending list, published on the 27th of May, 2025 T, 16 hours, 40 minutes, and 21 seconds, 0.0000Z. This paper, published about a month ago, introduces a new architecture that helps a model achieve an inference speed over 1,500 tokens per second per card. The paper is titled, Pangu Pro MoE, Mixture of Grouped Experts for Efficient Sparsity, and it tackles a major efficiency problem in a popular type of LLM called Mixture of Experts, or MoE. In these models, some experts get used far more than others, creating system bottlenecks. This paper's new architecture, Mixture of Grouped Experts, is designed to fix that by perfectly balancing the workload. So how does this new architecture actually achieve that perfect balance? Well, this diagram lays out the Mixture of Grouped Experts architecture. Input data first goes to what's called a global softmax router. This router acts like a traffic cop. It looks at the input and decides which experts, these are smaller, specialized neural networks, are best suited to handle it. Now, here's the clever part. Instead of just picking the top experts overall, the router is forced to select a specific number of experts from each group. This grouping is what guarantees a perfectly balanced workload. And this figure really drives home the difference that architecture makes. On the left, you see a standard Mixture of Experts model. Look how the work is spread unevenly. Device 1 has nothing to do, while device 4 is overloaded. But on the right, with a new Mixture of Grouped Experts, every device gets exactly 2 experts. This leads to the chart on the right, which plots the imbalance score, where 0 means perfect balance. The new MoGE approach hits 0 every time, while the old MoE method shows frequent, inefficient imbalance. So, building on that perfect balance, this table gives us the technical specifications for the model itself, called Pangu Pro MoE. The key takeaway is at the bottom. While the model has a massive 72 billion total parameters, which are the internal settings tuned during training, it only activates about 16.5 billion for any given task. This is the core benefit of this sparse design. You get the knowledge of a very large model, but the computational speed of a much smaller one, which is how it achieves such high performance. Okay, so getting that incredible speed isn't just about the architecture. It's also about deep system-level optimization. This flowchart shows exactly how they achieve that. The authors use a strategy called hierarchical and hybrid parallelism, or H2P, which is a sophisticated way to split the model's workload across many processors. Crucially, they also designed 2 custom fused operators. A fused operator is when you combine several small computational steps into one larger, much faster one. These are called mull attention and swift GMM, and they specifically accelerate the model's key calculations on the Ascend hardware. Okay, so all that system optimization and architectural design is great, but how does the model actually perform? This table answers that question, comparing Pangu Pro MoE against other leading models on a range of language and reasoning benchmarks. And the results are really impressive. Despite activating only 16 billion parameters, which is far fewer than some of the dense models it's up against, Pangu Pro MoE achieves top scores in many categories, including MMLU Pro, CEVOL, and mathematical reasoning. This really validates the whole approach. You get top-tier performance with incredible efficiency. And that efficiency isn't just about benchmark scores. It translates directly into raw speed. This table shows the performance during the decode stage. That's when the model generates new text, token by token. The key metric here is output throughput. The new Mixture of Experts model, at a large batch size, hits nearly 1150 tokens per second. That's almost double the speed of a standard 72 billion parameter dense model. With an extra acceleration, it even pushes past 1500. This really shows how its efficient design allows it to run much faster. So to wrap things up, this paper presents a really elegant solution, the Mixture of Grouped Experts architecture, to solve a major bottleneck in sparse models. That is, workload imbalance. By grouping the experts, they guarantee every processor stays busy and gets an even share of the work. This architectural change is the key to the incredible speed and efficiency we saw. And as the results show, this efficiency doesn't sacrifice performance, delivering top-tier results on tough benchmarks. That's all for this week's AI Research Roundup. Thanks for listening.